So welcome back, and now let's take a look at this modified example that shows us how we can move from pushdown systems to weighted pushdown systems. Now I'll be explaining that to you by basically modifying the taint analysis example that we saw earlier to an example that conducts a linear constant propagation. So previously I showed you this example here where we had a little tainted value that was passed through these increment methods that were basically propagating the taint. But now we want to do an actual linear constant propagation. So let's initialize this instead not to a tainted value, but to a numeric value whose constant value we want to track throughout the remainder of the program. Okay. And like I explained to you before, we're here looking at linear constant propagation. That's important because for pushdown systems and also weighted pushdown systems, we demand that the flow functions and also the edge functions are distributive. And as I explained in DECA 1, you get a non-distributive framework when you have a non-linear constant propagation. So here we're assuming only simple mathematical operations on single values, like incrementing, for instance. Okay, let's take a look at how this works. So looking back at the taint analysis that we conducted in the previous lecture, you may remember that we had such a normal rule here that would actually propagate a value, or back then it was a taint, right, for t from line 1 to line 2. And that was exactly what this particular rule here would actually express. Now, what we are adding here is to each such rule, we're adding a particular weight, and here we have a weight domain that is similar to what we also saw in IDE. Basically, the functions, function space over all integers, and so here we would actually, in this case, use a constant function that always returns 0, and that models the case that t here is definitely and independently of any other context in the program being initialized to 0, no matter what, right? That's why we have this constant function here. And in IDE, this would basically have been an edge from the initial tautological fact that you may remember, right, to t and with the same function, but here it's basically modeled through such an initial sort of self edge, right, that goes from t to t, from line 1 to line 2, yeah, with the same function. So it's a little bit of a different bootstrapping than we had it in IDE, but essentially it's having exactly the same effect. Now, what you see here is the next rule. So this is actually the push rule that we are having for processing the invocation, the first invocation of this increment procedure on the right-hand side. And this is telling us that the value of t at line 1, it's actually passed to v at line 5, right? That's what you see here, but in the context of the procedure call at line 2. Okay, that's also something I already explained in the previous lecture. And now what you see here is that this push rule, it's actually annotated with the very same function here. And this function at this point, it's basically taken from the previous function that we had already. So in IDE, you may remember at this point, we would have had so-called jump function, right, that takes us to this program point and already models the data flow that we have obtained until here. And you can think of it as this partial summary, this jump function that has already been computed until here. And we just saw this on the previous slide, right? That was exactly the same function. So we're using this here as well. And what this is basically telling us is that the variable v at line 5, but in this particular context, right? So in this particular context of line 2, that should be associated with this particular edge function that you see here, or weight function, right? Okay, now when you look at this in terms of the pushdown system itself, then basically now you will see that, so this relates to this part here, right? where we previously had T, L1, we now have V and L2 on the stack and L5 as well. Okay, so that has been pushed. Then next we are actually processing that particular procedure here, right? So we now have L5 on top of the stack, so that's where the processing sort of continues, right? And we now see that V, L5 maps to V, L6 because the value from here that's stored in V, it's being passed on to here. V is not changed, right? And the fact that the value, the numeric value also is really not changed is denoted by that particular function here. Just seeing I'm having a mistake on the slide. This should still be 0, right? I don't know what happened there. So this here is the identity function. And then down here, we have the data flow from V to R, right, at this particular statement. But this is now the sort of more interesting case, right? So this is really the situation where the value that is stored into R, it's incremented, right? So that's why we had this increment function annotated here. Okay. Then this is basically then also updated here, right? Because we have this, this rule that we have down here. And by this particular rule, what you will also see, and that's something I still wanted to make sure you all understand, we're basically moving this pushdown system into 2 different states, right? And that's something that is actually true for pushdown systems with weights, but also without weights, right? So the pushdown systems that are being used here, by the way we are using them, they are actually so-called non-deterministic pushdown systems. So that means that you can always be in multiple of these control states at the same time, right? And so just as you can have multiple variables tainted at the same time, or you can have multiple constant values that you are tracking at the same time, you can have multiple control states that this particular automaton assumes. All right. Yeah, and this continues like I just explained. So I think all the most essential steps I've shown to you. And what I already explained in the previous lecture is that there's this poststar automaton saturation algorithm that allows us to actually compute, basically a finite state machine out of this, which then determines reachability and therefore allows us to actually compute solutions to this particular analysis problem. And one of the major contributions by Reps and his co-authors was that they also showed in one of their papers that there is such a thing as a weighted poststar automaton saturation that, similar to how you would extend IFDS with IDE, actually computes these functions along the way as you are saturating your automaton. And I'm here going exactly through the same example that I had in the previous lecture, except that now we have these weight annotations here as well. And if you remember, V is actually the formal parameter in the call-Lee method, right? And this formal parameter, it can have any value depending on the particular calling context, right? Just in our example, it can actually have multiple different values at multiple different call sites. And so that's why at line 5, at the first line of the callee, it doesn't really have any known value, right? So that's why this function here is also just the identity function. Now, like we had before in the poststar automaton saturation algorithm, we're now matching this against the existing rules, right? And here we again have these 2 rules that match. And so we apply them, right? And so because of this first rule, we now have the situation that we have an edge from V to the accepting state, not just at line 5, but also at line 6, right? So basically I have 2 edges here now both of which are labeled with the identity function, right? Because we have the same weight here as well. And I'm just denoting these two edges here by one compound edge with L5, L6. Then due to the second rule down here, we are now getting another control state, control location also for R. And this is now connected to the accepting state with L6, right? Because we have an L6 here. And now we're using the increment function, right? So this is telling us that at line 6, the variable R has the same value essentially, but incremented by 1. Okay. Now let's take another look at variable t, like we also did in the previous lecture. So t at line 1, we know is initialized to 0, right? And that's basically encoded by what you see here, right? So it's annotated with this constant function 0. And again, we are matching this against the very same rules now, right? So this time, this rule header here matches that particular situation. And now when we apply this rule, we have a push rule again. So we again get the setup here that we also had in the previous lecture. So this is basically telling us the following. That's interesting now. So again, this is annotated with this particular constant function here, right? And excuse me, this is why this is also carrying over to here, right? So this is telling us the following. So in the context of line 2, v has actually the value 0. Okay, that's what you actually see here. And that's important, right? Because we want to be able to say in which particular situations, in which particular calling contexts, the variable actually has which particular constant value, if there is a constant value for this particular context, right? And yeah, then here, this is basically initialized here to the identity function itself. So this is just saying v at line 5 is basically having whatever value v is having at line 5. Now, this is then again matched against these two rule headers here. And now you can see again what's coming out of this, right? So for this particular, let me go back, excuse me. For this particular first rule here, we're now having the situation that we have a second edge from V to this state, also with line 6, right? So this is being added here. And due to this second rule down here, we actually have to add another node for R like we did earlier, right? And this is now again pointing to the same value that v, L5 was pointing to earlier, right? But this time with L6, and also this time annotated with this other edge function, right? Because this time we actually need to take the incrementation into account. Now, this new part of the automaton we can match against we can again match it against this rule. And yeah, this is again a pop rule, right? And so what happens now is that we basically follow this particular context here. We pop this off the stack. So that brings us to this state that you see down here, the original accepting state. And now we actually have to add x here, right? Because this is actually labeled with x. And yeah, because L6 has been popped, right? So this is now annotated with L2. So that brings us also to the accepting state. And now this is actually the interesting part. This edge here, what does it need to be labeled with? In this particular case, we're basically applying, you could say, the summary for the procedure. And then we are also applying it to the particular calling context, right? So this here you could see as our procedure summary, right? So the procedure summary for R at line 6, it's telling us that this particular value is being incremented when we actually call the callee procedure. And this context information here is telling us that in this particular context that we were inspecting, the one at line 2, the value, we actually had a constant input value 0. And now when we actually combine these two functions, so we do function composition like I'm showing you up here, then this actually results in the constant function 1, right? And that's then what this particular edge is actually being annotated with. So that's very similar to the IDE algorithm, where when you also process a return flow, you would then look up basically the different calling contexts, and you would apply the procedure summary to these particular calling contexts. That's exactly the same that we're doing here. And yeah, so this is not the entire poststar automaton for this example. In the example, we actually had 2 increment calls, so you would be doing exactly the same again for the second calling context as well. But here I'm not going to go through this because it's basically the same algorithmics and you get a very similar setup. And that's also something you can easily try out at home. To summarize, push-down systems, like I showed you, they allow for an optimized representation and evaluation of IFTS problems. So that's something we already saw in the previous lecture. We saw that you can have these normal rules that model regular flow functions, intra-procedural flow functions, and we have push and pop rules that implement flow functions at calls and returns. And this week I showed you how through weighted pushdown systems you can actually add some weights in a weight domain, and that then allows you to actually solve IDE problems as well. And what's really important here is that for both pushdown systems and weighted pushdown systems, the state reachability can be efficiently computed through this poststar algorithm, right? And so if you remember, that's also something I explained to you in the lecture on SPL lift, right? So if you assume that these operations on the weight domain, right? So like here, the combine and the extend operation, if you assume that these are constant time, right? So that they don't depend in any way on the size of the program or anything like that, then basically this added computation of within the weight domain, it doesn't really add to the computational complexity of the whole problem, right? So if you have a PDS problem, it has the same computational complexity as the WPDS problem, right? The weighted pushdown system problem, but only under this assumption, right? And as I explained to you in the case of SPL lift, for instance, we had the situation that we were actually keeping track of these feature constraints, and they could grow very large. And even if you represent them with BDDs, then some of these operations can actually become rather complex and definitely not constant time anymore, because the size of the constraint, at least to some extent, can grow with the size of the program. And yeah, then that's obviously no longer true, right? Then the weight computation does incur at least some limited cost, and it also factors into the complexity equation. Yeah, that's all I wanted to say about weighted pushdown systems. In the next few weeks, we will be continuing the discussion. We will be looking into first so-called demand-driven algorithms. So that's a special way in which you can compute well, iterative data flow problems, so fixed point iterations so that they can terminate faster in certain situations. And then we are slowly transitioning into the more applied part of the course where I'm showing you how to actually combine all of these principles like demand-driven analysis and weighted pushdown systems to synchronize pushdown systems, which we have then actually implemented in actual tools such as CogniCrypt, for instance, that I will cover in the second half of my course. Thank you very much for your attention, and I'll see you next week.